Swayam Prabha. Digital India. Educated India.
We talked a lot about, for 2 hours, we talked about force on a single particle, but hopefully I gave you a good historical perspective. I'm pretty sure you don't get all the details, but you get the big picture. Now you can read the details on the papers or the book, and you have better idea. Okay. Now, similarly, I want to now talk about another important thing, which is lift force, which is often very important when a particle is close to a wall. Okay, that's when it gets very important. But that's not the only time, because in cricket, baseball, everywhere, this lift, golf. Okay, in golf, obviously lift force is terrible, because just you end up hooking the ball or shanking the ball. But in cricket and baseball, that's everything. I mean, you are able to create a lift force. You aren't really talking business. Okay, so lift force is very important in sports, and of course deposition, resuspension, particle separation, a lot of it, lift force is important. So what is it? Okay, and how do we model it, and so on. Okay, so that's the goal. First, I want to talk about what is a lift force. How do you describe a lift force? Okay, so let's say you have a particle, and this particle is moving at velocity v, and let's say some fluid flow is happening, and this flow, it could be a complicated flow. I keep calling it UC. Let's use that term. Maybe I should not. I should draw this fluid velocity at a different angle. Okay, so it's moving differently from the particle. Okay. Now, in the particle's perspective, in other words, you put yourself on the particle frame of reference, then what you have is you have the particle, and as seen by the particle, you have fluid velocity coming. So this is uc minus v. That's the relative velocity. So in other words, as seen by the particle, you have a relative velocity, and you also have relative acceleration, and so on and so forth. Right? Now, drag force is nothing but, so if you have a force on the particle, the component of this force in the direction of relative velocity, okay. So if I call this direction to be equal to unit vector ER, ER is the unit vector in the relative velocity, F dot ER in the direction of relative velocity, that is the definition of drag. So this is what you will call drag. The particle experiences force in a direction which is not aligned with relative velocity, but the component that's aligned with the relative velocity is called the drag, and obviously the other portion, which is F minus drag, is lift. Now, I want to point out that you have already seen lift. We just didn't know about that. Okay, because when you remember, you had unsteady, quasi-steady, added mass, Bassett history. Only this guy is drag. Only that guy had u minus v in there. For example, added mass, its direction was, there are other terms in there. Okay. It doesn't have to be in the direction of relative velocity. In other words, relative acceleration need not be in relative velocity direction. Okay? So, in other words, these three forces, this guy, and this guy, will be, some of it you could call it drag, some of it you can call it lift, but this is not what I am talking about. This is not the lift I am going to be talking about. So, I want to point out that in a general sense, drag is in the direction of relative velocity, lift is perpendicular to that. Only quasi steady force will be purely in the relative velocity direction. The other forces could be in any direction, but that is not the kind of lift that I am talking about. I am going to talk about a slightly different lift. Okay? What happens when there is a shear flow or when the ball is spinning? What kind of lift? There are two kinds of lift forces I want to talk about, which is shear induced lift and rotation induced lift. Those are over and above all these things that I have written. So, they are extra, like bonus. Not good for modelers, but certainly those are the ones that I want to talk about. So, now we know what lift we are talking about. Okay. So, let us start with shear induced lift. So, our velocity is only in the x direction, and there is a particle. Now, you can clearly see that it is a steady flow. So, no added mass, no Bassett history, pressure is uniform. So, no undisturbed flow. So, you would have calculated, how would you calculate the drag force on this? It is only quasi steady, do you agree? And surface average, by the way, is the same as the center velocity, because velocity is higher on the top, lower at the bottom, so they average out. Okay. So, here is the drag, but in this case you can easily see that there can be a lift force. Okay. Because high speed, here there is low speed, Bernoulli equation says high pressure and low pressure, there is a lift force. Now, I am going to ask a question and I am going to prove that there cannot be a lift force. Okay. For example, let us say this shear flow, I decompose it into a uniform flow of this average magnitude, and let us say even this particle is spinning at some omega. So, I am going to break this into three problems: a uniform flow plus a shear centered about the particle plus there is no flow, just the particle is spinning. Right? We had a problem where there is a shear flow and the ball is spinning, and we are interested in what the shear does to the lift and what the spin will induce a lift force. Okay. And I broke this into three problems, which is just a uniform flow equal to the center line velocity plus some shear flow, high on the top, positive on the top, which adds up, and negative at the bottom, plus particle spinning. Now, I would ask you, if there was only this problem, would there be a lift force? This is, let us call it problem 1, problem 2, and problem 3. There cannot be any lift force, right? No lift. What about in the second problem? Why should it be pushed up? It will equally be pushed down. No lift. What for the third problem? no lift. So, some of these things there is no lift. So, what is going on?
Reynolds number not 0.
Reynolds number is not 0. This superposition is allowed only at Reynolds number 0. So, in the first point that I want to make is Stokes flow no lift. Okay, you put it down, okay, write it down. In the limit of Stokes flow, there cannot be a lift. Lift is only at finite Reynolds number, and the lift is due to interaction. These two guys talking, a shear and a uniform flow, will create Safman lift. Just a ball spinning in stationary in air just won't do anything. You got to throw it and give a spin. So, in other words, you must have relative velocity and a spin. In other words, you must have this plus this, and this is called Magnus lift.
Sir, but the linear shear won't create the rotation of the particle.
What is it?
Linear shear won't create the rotation of the particle.
Will also. The problem is complicated. I am just breaking it into pieces. Okay. So, you are right. A shear flow will make the particle rotate, and the rotation will cause lift. So, the problem is quite complicated. You are absolutely right. So, in real world, but if you think in terms of fairly large size balls, the shear won't create any lift.
But let's say Reynolds number equals to 0.9 or 1 won't create a shear like rotation of the particle.
Absolutely, yeah. So, in reality, a shear will create a lift force, but it will also make the particle rotate. So, there can be Magnus force, and they will change over time. You are absolutely right. So, problem is quite complicated. I am just trying to think of one at a time.
Okay. I am just talking about this Stokes linear shear in the Stokes range, that is less than 1.
Well, in the Stokes range, it will make the particle rotate, but there will be no lift. Okay. If the Reynolds number is 10 to the power minus 2, minus 3 like that,
That one,
there is no lift.
Equals to 1, I think.
Equal to 1 it will be.
0.9, 0.8.
Sure there will be. Well, of course.
Will create
If it is non-zero, technically the closer you go to 0, there will be no lift. Okay. The farther you go away from, as you approach 1 and above, there will be plenty of lift force. Okay. Yeah. So, the point is that it must be a nonlinear interaction between shear and a uniform flow, or uniform flow and particle rotation, the nonlinear terms will have to work. So, in other words, Reynolds number must be finite. It could be 0.9 like he points out, it could be 10, etc. You will have lift. So, now the theory people have worked. So, it is harder problem to solve. So, you can define two Reynolds number now. If you have a shear flow and a particle, this is relative velocity based Reynolds number. So, it is the diameter, u0 is the velocity at the center line. So, this is u0. G is the velocity gradient, du dy is g. So, you can write this as dp times g. So, the velocity is how much the shear velocity changes across one diameter. So, now you have two Reynolds number, shear Reynolds number and relative velocity based Reynolds number. Okay. Now, there is a lot of details. The classic work of Safman, he assumed this Reynolds number to be much smaller than this Reynolds number, and he did the theory, and I have gone through the theory in the notes. you have to solve the inner problem and outer problem. So it's a perturbation problem, singular perturbation problem. Okay, and the end result. This is inner problem, outer problem. I'm going to skip all these things, and the end result is shear lift force comes out to be 6.46 viscosity times Reynolds number square relative velocity g over nu f to the power 1/2, and it's directed in the lift direction, which is Ey. Okay, so in other words, let me just call this direction El. So in other words, the particle will experience a flow force up, and this is the formula Safman derived. This, for this Reynolds number and Reg, both Reynolds number must be small but not 0. If it is 0, then it doesn't work, but if it is small, so this is good. You can use it when Reynolds number is 0.9, 0.8, etc. But when Reynolds number gets large, this doesn't work. And this formula actually, to be correct, Safman assumed that this Reynolds number to be even smaller than this Reynolds number, but there is a lot of work done by Maclaurin. So Maclaurin is a really great researcher at Clarkson. So he extended this theory of Safman, and he derived a correction function, some function j epsilon, and epsilon is related to Reg to the power 1/2 divided by Re. Okay. So in other words, this formula was good only in a very specific. So I would use this formula. This is the modified Safman's lift force. It's good for any shear Reynolds number, any relative velocity Reynolds number, but they must be small. Actually, it turns out that this formula works really good even for fairly good size Reynolds number.
Just repeat the last thing you said about this.
Yeah, Maclaurin, this formula, so Maclaurin derived the empirically he derived. So there is a j function. I have given it in the book, so I'm not going to write it here. So you look at chapter page 106. Okay, I have given that function. It's a long equation. So basically, he just took Safman's work and he modified it a little bit, and he gave a good formula that works, gives you lift for any Reynolds number. All you need to know is viscosity of the fluid, radius of the particle, what's the relative velocity coming, and what's the magnitude of the shear, etc. And you have the force. Okay, so that's the lift force, and obviously this will go to 0 when Reynolds number goes to 0. Okay. Now this is for shear. Now you have similar formulas for rotation induced force. So in other words, instead of this, if you have a vortex and if you put a particle in there, this particle will experience a lift force up or down. Okay. So in other words, what I am trying to say is that the shear lift that Safman gave is good, because when a particle is in a boundary layer, it's like a shear flow, and that's what people use. But that's not the only lift force. That's the main point I want to point out. Okay. There are many other kinds of flow. So for example, the vortex induced lift force is it's roughly the same formula, but the devil is in the details. Here the vorticity in this flow, let's say is omega c. This, when you look at it, this looks exactly the same as what I wrote in the previous. Okay, instead of 6.46 and the shear, here you have 8 and vorticity. Okay, same kind of formula, but I just want to impress that Safman's lift people use all the time in so many different places, even in places where they are not really allowed to use. I just want to point out that it's most accurate only in a wall bounded, not wall bounded, it's in a free shear flow. Okay,
Bounded shear or unbounded shear?
In an unbounded shear flow. Safman work only in an unbounded shear flow. The exact derivation is for an unbounded shear flow. McLaughlin's correction is for an unbounded shear flow. So now, if you have wall, later we are going to talk about this, maybe this afternoon or something. I will talk about what effect wall has. Maybe tomorrow I will talk about how to handle wall. Wall will add another lift force, more complicated. Okay, so the business is really hard. Okay, yeah, it's almost time. So basically, I didn't have a whole lot of things to talk about lift forces. So the main point is that it's a non-zero Reynolds number, so you need to have finite Reynolds number. Now, just like in the quasi-steady drag force, we have finite Reynolds number correction. There are finite Reynolds number corrections for Safman's lift force. Okay, so you have to read the literature, and I have just given you some ideas that in a shear flow that there will be lift. Now, similarly, if a particle is spinning, then you will have spin-induced lift forces as well. So the details, a lot of details are there, but I'm not going to cover those things. Okay, so when a particle is in a shear flow and it is rotating, now you have two kinds of lift forces. They can cancel each other, they can reinforce each other, and you got to be very careful. So you have to take into account what is the shear that the particle is there, how much the particle is rotating. So it's a fairly complex business, but there are lots of work, lots of formulas that people have written. Some of them are given in my the book, so you can consult it and use it as an add-on to Bassett with a BBO or MRG. So you have already 4 forces there, plus this is the 5th force you have to think about. Okay. Now, this is not the end. You may have turbophoretic forces, you may have electrostatic forces, etc. So they are even on top of it. So I'm restricting myself to hydrodynamic forces, what the fluid does. But you may have other external forces, magnetic forces, and so on. So you have to add all of them. Okay. Any questions?
That was just one question. You see that it is the relative velocity, right?
Which one?
The
Yeah, always relative velocity. The reason, it must be Galilean invariant. Okay. So for example, shear, you move around, the shear doesn't change, the g, but velocities always have to be in terms of relative velocity. For the model, the Safman lift force model, to be Galilean invariant, it must be, though I wrote only UC because I assumed stationary particle. If the particle is moving, then you have to replace it with the relative velocity. Excellent question.